Okay, so moving on to our next conic, which is the ellipse. So we're going to look at ellipses today. As I mentioned before, an ellipse is when we just slice a cone at a little bit of an angle. So it's kind of like a stretched out circle or an oval. And there are two different directions in which we will see ellipses today. What are some application to ellipses? Well, first, what is an ellipse? So besides just slicing a cone at an angle, it's the set of all points in a plane, the sum of whose distances from two fixed points, called the foci, is a constant. So again, this is like a circle that's stretched out where if we bring the foci closer and closer together to the middle, it will now become a circle. But as soon as we have two separate points stretched out, now we have an ellipse. And they could also stretch out in other directions. It does not just have to be horizontal. So besides the mathematical properties of the ellipse, the foci have important properties as far as reflection. So one place is the U.S. Capitol building, where if one person is located at a foci and another person is located at the other foci, the person at one foci can whisper and the person at the other foci will hear exactly what they are saying. But anywhere else in the chamber, you will not. There's also an example of this at the Museum of Science and Industry down in Chicago, a whispering chamber. And the St. Paul's Cathedral in London has an elliptical area as well, where if one person is at one focus and another person is at another focus, they can talk to each other. Or you could eavesdrop on other people, as you can see this little story about John Quincy Adams. An application to ellipses is in getting rid of kidney stones, which hopefully none of you have had. But anyway, they use the property of the foci to put a person and the kidney stone at one foci and send a shock wave from the other foci, so all of the energy is focused on the kidney stone, and it will destroy the kidney stone. Okay, now let's move on to what we're going to do with ellipses. So we are essentially going to do exactly what we did with the circle. We're first going to look at the standard form of an ellipse. So an ellipse has a center at the point HK, just like a circle. There are two very similar but slightly different standard forms to the ellipse. Now, one thing I want to point out is don't get so focused on the A versus the B versus the C and whatnot. Really actually try to understand the ellipse, and it'll make this much easier. So when we talk about a horizontal major axis, we're talking about an ellipse like what we saw in the picture. That's a horrible ellipse, but we'll have a center, so this will be the point HK. I have A, which is the distance from the center to the major vertices. So essentially just whichever way the ellipse is stretched, that is the major axis, and then the shorter distance is the minor axis. So I would have some point here and some point here. These would be the major vertices. And this distance here would be the distance A. So then on the top and bottom, I would have the minor vertices. And this distance here would be the B. So that's the distance from the minor vertices. So 2 times A is the length of the major axis, because A is from the center to here, and A is from the center to here. So 2A would be the length of the major axis, 2B would be the length of the minor axis. So what is this C? C is the distance from the center to the foci. Where are the foci? Well, the foci are somewhere along the major axis. In this picture, I don't know exactly where they are, but we'll say that I have one of them here and one of them here. So this distance right here would be the distance C. And that is my foci. Okay, how do I find C though? Well, how do I find any of this stuff, right? Good question. Well, there's a nice relationship between A, B, and C, and that is A squared minus B squared equals C squared. Very similar to our Pythagorean theorem, but it is not our Pythagorean theorem. You could prove this to yourself by drawing right triangles and fun things like that, but for now you could just take my word that for an ellipse only, the relationship between A, B, and C is A squared minus B squared is C squared. So real quickly over here, we also have the vertical major axis ellipse. So this is the same thing, but now it's stretched more vertically. So I'm still going to have a center with the point HK. I will still have my major vertices. Now they are going to be vertical. So this distance here is my A, and I will have my minor vertices. They will be now horizontal, and this distance here will be B, and then I will still have my foci along the major axis, and so this distance here will be C. So it doesn't change whether you're doing horizontal or vertical. And so as I said at the beginning, don't get so caught up on which one of these values here is A and which one is B. The larger value is A, or if it's in standard form, the larger value is A squared. The smaller value is B squared. Whatever number is underneath the X term goes in the direction of the X's. So horizontal, that's X direction. So that's why the horizontal major axis will have the larger value under the X squared term, whereas the vertical major axis will have the larger value under the Y squared term because Y values are vertical. So personally, I think that's an easier way to remember this. Okay. So now let's do some examples. If I have x minus 2 squared over 64 plus y squared over 9 equals 1, we want to find all this information and we want to graph this. So we know the center is the point 2, 0, because this is x minus h, y plus k, or y minus k squared, but there's nothing there, so that's a 0. Since this number is larger, 64 is larger than 9, I know that a squared equals 64 and b squared equals 9. So therefore I know a is going to be 8, b is going to be 9. Now, watch what I do here. I'm going to graph this before I find this information. So we're going to use our center, which is the point 2, 0. A squared was 64, so therefore A equals 8, B equals 3. So from the center, I'm going to go to the right 8, and I'm going to go to the left 8. Those are going to be my major vertices. So now I can come down here and I can write that the major vertices are the point 0 and the point -6, 0. Now I'm going to go up and down 3. Those are going to be the minor vertices. So I can go ahead and write those are 2, 3, and 2, -3. Now we can go ahead and draw the ellipse. Now we want to find c squared because we need to find the foci. So I know 64 minus 9 is c squared, so 55 is c squared. Therefore c is the square root of 55. So what is the square root of 55? Well, that's 7 point something, so it's going to be hard to graph here exactly, but it's going to be like there and like there. And to write my equation, I know that I just added this value to the x value of the center, and I subtracted this value from the x value of the center, so I'm going to have 2 plus root 55, comma 0, and 2 minus root 55, comma 0. And so again, I knew that because since it's a horizontal major axis, the foci are going to relate to the x value of the center, and the y value won't change. If this was a vertical major axis, the foci would relate to the y value of the center, and the x value will not change. So this would be my graph. This would be my information. I want you to try that with the vertical ellipse over here. So pause the video, find the center, the major vertices, the minor vertices, the foci, and try to graph. Again, do the graph first to help you find the vertices. That's easier, I think, using your A and B values. Or again, don't even think of it as A and B. Think of it as the number underneath the X and the number underneath the Y goes with the X and the Y, respectively. Alright, pause the video, try this on your own. Okay, so for our major vertices, we should get the point negative 310, negative 3, 0. Minor vertices are negative 1, 5, and negative 5, 5. Our foci are negative 3, comma 5 plus root 21, and negative 3, comma 5 minus root 21. How do we come up with that? Good question. So, we have a center of negative 3, 5, because I have x plus 3, so the center is negative 3, y minus 5, so the center is plus 5. Underneath the x's, I have 4, so that means b is 2, because the square root of 4 is 2. Underneath the y's, I have 25, so a is 5, because the square root of 25 is 5. So I plot the point negative 3, 5, and then from there I'm going to go up 5 and down 5. That's how I got the major vertices. I go to the right 2 and I go to the left 2. That's how I got the minor vertices. A squared is 25, b squared is 4, a squared minus b squared is 21. So the square root of 21 is c. Since the major axis is vertical, the c value is going to go vertically. So from the center, I'm going to go up the square root of 21, and I'm going to go down the square root of 21. So the foci was negative 3, comma 5, plus or minus the square root of 21. Okay, what about the general second degree equation? Good question. What makes the equation an ellipse? Also good question. So what do we want to look at? Again, we're going to focus on the A and the B. So what do we need to have happen? We need A does not equal B, but A and B have to have the same sign. So they either both need to be positive or they both need to be negative, but they cannot equal each other. If they equal each other, then it's a circle. So we want to identify the conic, write the conic in standard form, identify the key components of the conic. So if it's an ellipse, which this is, spoiler alert, then we are going to want to identify the foci, the center, the vertices, all that fun stuff. What do we do? Well, we see that these two values have the same sign, but they are not the same value, so we know this is an ellipse. Now from here, follow the same process as the circle. So we are going to group the x's and group the y's and bring the constant over to the other side. Now here, and this is where the circle was unique, since the coefficient in front of the y and the coefficient in front of the x are different, in order to make the leading coefficient 1, I actually want to factor out the leading coefficient from the x's and factor out the leading coefficient from the y's. So my next step, I'm going to write this as 9 times the quantity, x squared plus 4x, leave a little bit of space, plus 4 times the quantity, y squared minus 6y, leave a little bit of space, equals negative 36. Now we will complete the square. Half of 4 is 2, 2 squared is 4. Half of 6 is 3, 3 squared is 9. Here, we're going to go on to part 2 of the video because there's an important thing to explain coming up next. So go to part 2.